You know nothing, Jon Snow. The jokes just write themselves with this one. In this episode, we bumble our way through an overview of zero knowledge proofs, another entry in cryptography's long line of mind benders. Zero knowledge proofs come from one of the most consequential decades in history for nerds like us. Forget classic rock and the emergence of hip hop. The cryptographers were the ones really cooking from the mid 70s to the mid 80s, with incredible bangers like public key crypto, Diffie-Hellman key exchange, cryptographic hashing, and of course, the beautiful Merkle trees that gave us our blockchains. After that, though, zero knowledge proofs were kind of shelved. But if there's one thing crypto and Web3 have been good at, it's inventing abstract new problems that need a nifty technical solution. So, what are zero knowledge proofs? How do they work, and what do they unlock for builders? We can't promise you'll come away from this episode knowing a lot, but hopefully it's more than zero. It's worth a shot. This is Not Your Crypto Podcast. Hello, and welcome back to Not Your Crypto Podcast with myself, Justin, and
Michael,
Ed.
hello.
So it's
I was
been a
quicker
while.
that time, I think.
That's your world record, actually, in response time. Every time it's Stockwash. It's been a while for some understandable reasons due to where I'm located. At the time of recording, there is a lot going on in the Middle East, to say the least. So, yes, we've had a larger gap. And then also because the topic we've decided to actually tackle finally has required a bit more extensive research, as per usual, because, we know nothing and now we want to know something, and so it takes a bit of time to get to understand what's going on before we record
You
and
might
talk
say
about it.
we had zero knowledge.
Yes, we had zero knowledge on hand, and that's the perfect prelude or segue into it. Michael, what are we talking about today?
We're talking about zero knowledge proofs, I guess, or kind of what they are, and but particularly what their application is to Web3, to the kind of blockchain world, and what that means, I guess.
Yeah,
I think honestly, zero knowledge is one of the earliest topics I remember us talking about
yeah,
with crypto a long time
100%.
ago,
Yes.
years ago, and they were as confusing to me then as they are now, I
Yep.
think.
And
I
that's
don't know
fair
that
because I'm just as
yeah.
confused as you. So we're going to try and fumble our way through this for the sakes of our listeners. I mean, to be honest, in all seriousness, we're tech heads, we're geeks, and so we find this kind of stuff endlessly fascinating. But this has been for Michael and I can say this, I can speak on our behalf because we were there together in the trenches trying to watch YouTube videos, understanding exactly what's going on here when we first came across this topic of zero knowledge proofs. And we've alluded to it in previous episodes. I think it was the Odd Couple where we talked about zero knowledge proofs being used to bridge Web 2 and Web 3 ideas and technologies. Zero knowledge has been around for a while,
Mhm.
and it's been around for a lot longer than even Michael and I realized or anticipated, and we'll get into that in a second. But why do we find it interesting is because when we first came across it, the both of us, one of the things people kept trying to explain is this offhand example of, well, imagine you're trying to verify your age to a website, but you don't want to reveal your age because the website's access is age gated. So you have to be over 18, over 21, over 25 in order to access it. Well, zero knowledge proofs allow you to say I'm over 25 without actually giving it your birth date. And then Michael and I did confused Pikachu face because we were like, well, how do you do that? And then the next level down explanation is, well, it's because you have a secret, and zero knowledge proofs are about verifying that secret is true without the secret ever being exposed. And then we're like, to who? And it's like, well,
Mhm.
the thing that's trying to guard access. Well, then how does the thing that's trying to guard access know
Yeah, I
that
think
you're telling the
like to
truth?
me this is we've talked a bit about before about how these kinds of areas kind of grind our gears where like you try to learn about something and there's like a surface level explanation that you get that is like endemic and everywhere,
Yep.
and you're trying to then you're like, okay, like cool, and it's like, yeah, I mean, it's your example, right? Oh, it's like you want to like it's like you want to verify your birthday without actually telling what your birthday is, or verify how old you are, or that you're above a certain age
Mm-hmm.
without revealing your birthday or whatever.
Yeah.
Now you understand zero knowledge proofs, right? And it's like, well, no, I don't actually. It's like, and then the other thing you can find is, implementations on GitHub, like papers, like I don't know, whatever. But it feels like there's like a missing middle of these explanations that connects like
Mhm.
the surface level to like the details, and that's kind of one of the areas that that we like
Yeah,
to
that's
try
where
and
we like
shed
to
some light
play.
on, right?
And it's because of who we are, right? Because that's where security professionals play anyway. The stated assumptions versus the actual implementation. It's that gap where things can go wrong, and that's that gap where it invites opportunity. You look like you want to say something.
Yeah. No.
Oh,
Yeah, you got it. Yeah.
and so here we are. So today we are going to talk about zero knowledge proofs. And so again, I'm going to go through a lot of nomenclature. I'm trying to make sure that the intention of this episode is that our listeners walk away with as basic an understanding as Michael and I have been able to scratch our way through with all the literature that's out there. But if you're a dyed-in-the-wool cryptographer, this is going to be way too high level for you. And number one. Number two, for all our mathematicians out there, we're not going to go into the maths. I promise you the maths will not get touched with a barge pole because we will only mangle them. But at the same time, we do want you to have a better understanding of zero knowledge proofs and what they do and the context in which they arose and why they kind of peaked why they've been not even peaked, but why they've been adopted with such gusto in Web3 world as opposed to what happened in Web2, which is, there's a reason for everything. And so let me take everyone back to around the mid 80s. Mid 80s, where it's a time where you've got mainframe, well, not even mainframe computing now, you've got networked computing, you've got your token star topologies. If anyone remembers their computer science degrees, you've got ring topologies, and you've got time shared computing. At this point, you've got authentication protocols. And people started to realize very quickly, especially when the data packets are going around in a ring topology that they're being shared with everybody. If you have passwords going across the network in clear text, trying to access gated resources, you could have a bad actor that intercepts said packet and gets access to said resource that they shouldn't be able to. So people started trying to come up with basically secure password protocols and ways of being able to validate that if you have a secret to access a thing, that you do not send it across the wire in clear text. So that's where you get the concepts of hashing from and encoding and encryption in general from. So cryptography has always played alongside computer science as well. They're quite tightly correlated. You'll see this because obviously if you go into the history of computing from the UK, especially with Bletchley Park and the code breakers, that was basically where computing grew up in the UK, and that came out of that whole Cambridge set where basically they were trying to break World War II codes, and they needed computers to do it. There's a fascinating story about actually sidebar. It's an absolutely crazy,
Cool.
fascinating story that may enrage a lot of British people when they actually found out what we did to the machines that were able to break the codes, and what actually the second order effect of how that set Britain's computer industry back about 3 decades because we didn't want to share the machines that were able to break
Oh, I do not know
codes.
that story.
Yeah, it's absolutely fascinating. It's on Wikipedia. It's kind of crazy. Like, it's literally alternative reality type situation. We did not do what we did. Could we have had our own Silicon Valley, a real Silicon Valley? Anyway, so 1980s, you want to share secrets. You don't want the secrets to go across the wire because you don't want the secrets to be stolen by the other person. So what do? Well, you come up with all types of white papers and ideas. And one of the things that fell out of this ideation period was ZK proofs. And the whole purpose of zero knowledge proofs was, how about instead of doing all these crazy things to the password, like hashing it, encrypting it, encoding it, and doing all of these things to make sure the wrong person doesn't have access to it, how about we don't send it at all? And everyone's like, oh, Pikachu face. So what happens here is the whole point of a zero knowledge proof and why it's called zero knowledge is you have two parties involved in a transaction, and you have one party, party A, we're going to call them the prover, the person or the entity or the system that wants to get access to a given resource. They have to prove that they know a secret or they are allowed to access said resource to the verifier who's in charge of gating access to this resource without the verifier actually knowing what the secret is. I'm going to let that one sit for a second in the air because this is the bit that broke mine and Michael's brains when we
Yes.
first came across it. How do you have a secret, prove you have that secret, but never share what that secret is to the verifier without fooling the verifier, without being able to spoof it? How is the verifier even effective at its job if it never receives the secret to validate that you are sending the right thing? Well, this is where it gets. So this
Yeah,
is
like
where
it's
the
hard.
problem.
It's hard to make this like semantic. Like it's hard to make the words you say when you talk about these things like mean something, right? Because our whole understanding of the context and the context of like identity and identity on the internet and stuff is like really heavily tied up in a shared secret model, right? So
100%.
like um yeah, and when you were talking about it, it made me think how closely tied the concept of and how like motivating the concept of like identity on the internet is
Hmm.
to all of these concepts, right?
Yes.
So like yeah, like your typical model of it is you know who I am on the internet because we both share a secret. The secret may be like a password. Like if I'm
Hmm.
proving my identity to a server,
Hmm.
the way I prove that is um, the server says, okay, only this person knows this secret. The secret is here in my database or whatever. And then I supply that secret, and they're like, okay, well, only that person knew that, so therefore, that's the identity, right? The
Hmm.
identity is tightly tied to like knowledge of a secret, and like a lot of identity models um, are derived from that, or like are kind of downstream of that.
Yes.
And this like takes that fundamental part of it and like just says no somehow. Like it says like and so then you kind of have to think differently about what an identity means on the
Hmm.
internet
Yep.
in order to like, at least for myself, I think,
Yep.
in order to like um kind of bootstrap your understanding of this thing.
That's
Because if you come to it thinking, oh, it means a shared secret, then you're like, well, what do you mean the verifier can't know the secret? Then it can't
yeah.
know who you are.
Yeah.
But the way to conceptually get around that is to not think anymore that who you are is knowledge of a secret. Who you
Yeah.
are is instead attributes um, about your self or your
Hmm.
context that you can um, prove to a verifier,
And
kind
you
of
know
thing.
what's amazing about you coming up with that mental model of trying to wrestle with the concept is basically what you need. What you've done there is you talk about identification and verification process, and that's when you start to realize that zero knowledge as we have experienced it as security professionals isn't really a security protocol at all. It's a verification protocol, and the key is in the name. And I was thinking this for a
Mm,
long time when we kept coming across the different concepts. I was like, I think my reason I was tripping up on it is because I'm looking at like a security protocol where you've got two parties or end
yeah,
parties, and you're trying to validate a thing, and then you give authorization for said thing. How about you look at it as verifying a thing and look at it as almost a verification protocol? And then that's where the privacy angle comes in, which we'll come into later, because one of the main applications of zero knowledge proofs that was sold to the world when it became a big thing around 2015-16 with the invention of ZK snarks, a subfamily of zero knowledge proofs. It was, oh my God, we can do all these crazy privacy things. As again, back to
yeah.
that age verification
Yeah.
example is
Yeah, I think that's
you
a
don't
good
have to
call out.
disseminate.
Like the way that you see the concept of zero knowledge proofs is going to change depending on what kind of like problem you're fitting it into as as a solution, and I think we'll
Yes,
talk about that in a little bit.
we will.
But yeah, I think the other thing I would say up front is like we've talked before in a few episodes about things that feel like they shouldn't exist but like do exist. I don't know if you
Yep.
remember this.
Yes, I
And
do.
I think I like listed a few of them in a previous episode. I forget if
No,
ZKPs
we put
were
ZK at
one
the
of them or
start.
not.
I think ZK was the head of
Yeah,
that
but it's
list.
absolutely one of those things that feels like it should not exist. Like you
Yeah.
describe it and you're like that's not possible.
Yeah.
And then like um you know it turns out that it is possible,
Yeah.
and there's just a lot of things like that.
Yeah,
And one of those things
exactly.
like that, which is an example that I think maybe can also be used to help understand like the concept,
Hmm.
which is closely related, I think, which I was like texting you about or something, is like public key cryptography, right?
Hmm.
So like I don't know if this is like a formally correct thing to say that the way we typically use public key cryptography can be like very comparable to a zero knowledge proof.
Hmm.
But like if you think about it conceptually, it's like I know a secret being the private key.
Yeah.
I can deliver a message to you
Hmm.
that is signed in such a way that I reveal to you that I'm the one who knows the secret.
Yeah.
But I don't actually reveal the secret to you.
Yeah.
the whole thing about, public key crypto, asymmetric crypto is
Yeah.
there isn't a shared secret,
Yes.
but you still know that I know a secret. I know that, and the thing I know is the secret that signed this message.
Yes.
So
And
like
so,
you learn the attribute
mhm,
of my identity. The attribute of my identity is that
yeah,
this message is signed by the person who knows the corresponding private key for this public key, but you
yeah,
don't know the private key. So like
100%.
there's a conceptual way in which that is correlate, like, I don't
It's
know,
not even
correlated.
correlated. In my research, PKI is seen as a subset of zero knowledge
Okay,
proofs,
great.
and there's
Yeah.
a
Okay.
bunch of
Sure. Sure. Sure.
protocols where you see like, well, that is zero knowledge because nothing is transmitted about the secret. The secret is not transmitted itself, but maybe attributes are and things are, and that's validated. And so the first question is, okay, how does this even exist? Why does it, like you said, how does it exist? I've just told you why it came about in 1980s. People didn't want to share password. They came with security protocols. Why was it never widely adopted if it's that old? Because anyone in the industry would be like, well, I only heard about this thing in 2015. It's like first white paper came out in 1985. It was then improved upon in 1986. You had interactive zero knowledge proofs. We're going to get there in a second. Then you had non-interactive zero knowledge proofs to basically lighten the computational load, and then nothing all the way until 2000s. And part of the reason that is because of the way the actual protocol operates. It's very computationally heavy, and at the same time, the white paper for hashing came out, hashing algorithms, and everyone was like, job's done. And walked, just, I'm not playing with this anymore. Kind of dropped zero knowledge proofs down. It's like hashing is just as good a solution for what the problem we're trying to solve. And so I'm going to delve into a little bit as to why is this thing computationally heavy, right? And it's
Hmm.
partly because what happens in zero knowledge, and when you've got your prover and your verifier, which I kind of want to get away from those terms because I kind of want to keep it simple. If
Okay.
I'm asking Michael, or my client is trying to get access to Michael's server, and they're operating on a zero knowledge protocol. My client has the secret, the server does not, and it's never going to get it. But the server is in charge of gating access to that resource. So what they kind of do in a mathematical abstraction kind of way is the server basically asks my client a series of questions, and this is in interactive zero knowledge proofs. This is in old school. This is not how it works today, but in old school, this is, I'm explaining this so that you get a basic understanding of it. Is
Hmm.
it asks a series of questions of which the answers display, if you have the right answers over a certain amount of questions, and if you have the right answers, it's probabilistically impossible that you are lying about knowing the right answer. And so that is where the linchpin comes in here. It's probabilistic. This protocol is in its mathematical makeup. It's about basically verifying that you know something, but you're unable to actually be lying about how you know about that thing. So what happens, to put this in a more concrete example, it's, imagine Michael's server asks my client 20 odd questions, or it can be any number of well, it can't be any number of questions because they're computers, so it's going to be a finite number of questions. But basically a set of questions where it's like, okay, if you, well, basically they could be binary in nature, yes, no, whatever, and over a number of times you're basically answering correctly. Sorry for the overuse of the word basically. If you answer these series of questions correctly, it proves to Michael's server that you actually do have the secret, and that's the way the secret is never shared. That is really weird, and it broke my brain for the longest amount of time, because the next logical question is, how is Michael's server able to verify that any of the answers to that question, those series of questions, are correct
And
if it never
is
has the secret?
there, so this is maybe a question, right? Like,
Hmm.
and I wonder if this is where I get tripped up a little bit sometimes on the zero knowledge stuff. Like you say, prove that I know the secret.
Hmm.
Um, is that right? Is that like a little bit too simple, or is it like prove that
Mm.
I can use the secret to demonstrate some other attribute, some
Okay,
other
you're hitting
assertion?
on why this is such a confusing topic from a security perspective. Yes, because this thing has so many applications, it depends on the context through which you're looking at it. Because really, fundamentally, all you're actually proving is that you computed a formula
Yeah.
and you got the right answer without sharing the answer. I
Yeah.
just know you got the right answer
Yeah.
because it's basically a balanced equation. And so what's happening in that question setting is, oh, you did have the answer to one of the main components of that formula, but you never shared it with me. And so I know you did the right math. Does that make sense?
Mm-hmm.
So that's
Mm-hmm.
why in a security setting, that can become a secret, right? It can be a secret
Mm-hmm.
that's never shared because, oh, you derived some number, used it in the formula, and the formula balances out without sharing the number with me. Because if I put in other inputs, because of the magic, I think, of polynomial equations and exponents, I'm able to
Yes, the
determine.
verifier can verify. It's like similar to. I mean, it's kind of in a conceptual way similar to the hashing stuff or to the asymmetric crypto stuff, in that the verifier can verify without having all the inputs, or
Yes,
without like
without
yeah,
having all the inputs or having different inputs that have bear a one specific type of relationship to the original secret.
yeah,
So under a security context, it's okay, you actually do know the secret. Under a computational context, it's I know this program ran as it should be, untampered with, and it's produced this output. Or it's, oh, I need a bunch or a series of calculations done, and I need them done in a special machine, but I don't want to have to validate whether you got the right answer by running those calculations myself. You should get to an output. So yes, you are seeing the link to hashing and all of that because
yeah. Okay.
they came out around the same time and they are kind of offshoots of the same Mac. So basically, that's what we're talking about here is Michael's server asking my client a bunch of questions. And we kind of just skipped ahead a bit with Michael's very insightful question there, which is a great question. But it basically depends on the context you're looking at, and therefore that dictates the application in which you can use these things, which is why as a security professional it's confusing, because I came at this as a security protocol and it's not. It's more of a computational protocol that allows you to verify things without having to share things around. To actually, you can just basically check whether something is run as it was intended to, and if the answer is correct without actually having to do the math yourself.
Yeah.
So there, back to the thing. As I said, that's kind of that was the thing that I tripped up on, was how does the verifier know that any of the answers to these questions are correct if it doesn't have the secret? And it's because of what Michael and I just discussed, which is these questions in reality are kind of like they're effectively formulas. It's I'm trying to think of a best way. Binary space would basically be, oh, Michael, is the head, is the, I don't know, if you've got a coin, does the coin have head and tails on it, or is it a one-sided coin or a double-sided coin type thing? I'm trying to understand. I'm trying to come up with a real-world example where you'd end up where one of the, it's what 50% or one of the answers effectively, where basically I ask Michael's server asks my client, um, is the building to the left or the right of a road? And I say right, and then it basically says, is that building north or south of this place? It's a series of questions like that. This is not how it's implemented to this day, but this is just an abstraction of what this process looks like when it's actually going, this interactive ZK proofing.
Yeah.
At the same time, you never talk about the building's name. You're just effectively saying where you're trying to validate you actually know the building's name through a series of these abstract questions. So that's the abstract nature of how it works. But the problem you have here is, and this also answers the question as to why it never popped up before mid-20s, is because computationally it is a very heavy process to just ask all those questions back and forth, especially on a network. You have jitter, you have packets falling out, and so forth and so forth. From a
Mhm.
UX experience, it's an absolute nightmare if you're trying to authenticate and all you want to do is verify you have the right credentials in order to access this resource. So again, that was one of the reasons for one of the reasons why it wasn't widely adopted. The other reason, and digging deeper into that reason, is kind of where we need to go next, because I kind of gave an example of north, south, east, west, because I was trying to do it in a binary way, because computers count in binary ways. But this stems from a branch of cryptography where it's not binary, and they use these things called arithmetic circuits. We're not going to go into those in details, but basically what you've got to imagine is you want to make sure that in order to reduce the probability that my client is lying to Michael's server, that it doesn't have to ask a whole series of questions, because as you said, computation is heavy. How about it asks one question where the possibility of answers is very large? Ideally, in an ideal world, ideal universe is a computer type thing here. It would be an infinite set of numbers or an infinite set of answers that can be correct, and you want them to choose the right one without revealing their secret. but at the same time, it's just one question. But you can't do that because computers have a finite amount of memory. So now you need an extremely large set of numbers or answers, possibilities to Michael Server's question. That is where this becomes very computationally heavy, and also why it's never been integrated. It wasn't really implemented and integrated into Web 2 world, because the number space, or the possibility space known as the challenge space, sorry for all the technical terms, but they're needed so that you can hang on to stuff, needs to be large. We're talking very, very large. We're talking 2 to the 128-bit, like we're talking very, very large spaces here, very, very large numbers. Just to put that into context, your average Java language, Java can hold 64-bit integers, I think, at max.
Okay.
And even back, I think C was like 32-bit integers. So we're talking huge numbers in which you've got to ask a question of which you're supposed to select an answer from in order to prove that you know the secret. So that was also another reason why it was like, okay, this is not computationally feasible because we don't have languages that can handle these numbers without specialized processors, etc. So why are we doing this? Hashing does the job. So I'm kind of trying to ground it into why we haven't seen it into now, because you can't divorce the invention of this thing from the time it was in. And I also want to keep that thread going at the same time. Michael, where are we? You good so far?
Maybe. Yeah, I mean, I think so. Okay, I think I can kind of make sense to me. Like you're kind of collapsing the iterative, like instead of having a series of questions that are, I guess, are you saying those series of questions are like kind of binary, right?
Yeah.
So like instead of having a series of questions that are more binary, you kind of collapsing it into one question or one proof that is like higher dimensionality.
Yeah.
And so that's kind of that's like a like almost like a compression
Yes.
kind of compression along the axis of how many questions you are asking.
Yes. 100%.
So I think that makes sense.
Yeah.
I still have a mental hurdle despite me saying all that stuff before. I still have a mental hurdle around the like proving that I know the secret statements, because in my mind it's like from the verifier's side, what does the verifier end up knowing at the end of this?
Okay.
It knows it ends up knowing that I know a secret, but it needs to like differentiate that from, but it like without knowing the secret itself, it needs to differentiate that from everything else.
Yes. And that's why the reason why you're getting stuck there is because you want the meat of this, which is the math. And it's the math that I don't want to go into.
But I don't think that I want that.
That's the only way you're going to get there, because I was in the same place you were for a while. And basically, it's the math. So what I've abstracted away here is, obviously, you ask this question that has a binary response. Really and truly, these are actual relatively complex equations that need to be balanced on both sides. And so without going too into losing our listeners and losing myself, what you're doing here is there's a publicly known formula from the outset that is known to both the prover, my client, and your server. They both agree this is the formula. You plug numbers in, it should balance on both sides. What I then do as the client is I create a number that is derived from said secret. So I create a number and I plug it into that formula. Now, because the formula uses exponents, that number that's derived from the secret has to basically be part of a formula that balances. And what you can do as the verifier is you can swap in and out other numbers to balance the formula, whereby it verifies that, okay, if this balances, that person must know a number, because this exponent could only have been this number, basically, because it's derived from this number. So it's it's weird. It's really, It's like you do with the large primes effectively as well. So, you have large prime numbers. It's a similar using modular math. And that's why it's able to do that, because it's saying, okay, this is a formula, it's got exponents, these are the properties of an exponent. If you derive a number from it and plug this number in, it balances on that side, it balances on this side. If I put in different numbers and get the same balance, because my client server initially supplied this number and it balances, Therefore, they did the computation correctly and they know the secret without me having to know it, because I was able to plug in other numbers and it balanced, and it can only balance in one of X amount of ways. That's kind of my understanding of it.
Okay. Okay.
And so that's why it's like, oh, yeah. If you don't get in that bit, it will never make sense to you. And
Yeah.
it took me a while to get my head into it. So
Mm-hmm.
yeah,
But like
so
the probabilistic part makes sense, and
mm,
I think there's like an intuitive sense that makes, because like in a way, all of crypto stuff is probabilistic, right? It's like like
yes,
everything has a key space.
yeah,
Any random guess could, to some vanishingly small degree of probability, result in having the right key,
yeah.
or knowing the C or whatever, right? So like the probabilistic aspect of it makes sense, I think.
Yeah. And so I mean, I can go into the details of the handshake between the two, my client and your server, but I think we'd lose people. But long story short,
No, yeah,
you
let's keep
generate this
rolling.
large number, you do the math on it, and then that's sent to the verifier, etc. And then the verifier basically says, okay, from there, I'm going to send you another number back. And then they do the math and they balance the formula, and it proves that you actually know some number. And there's reasons why that happens, and I won't go into the details of that, but that's basically what's happening. Is your server's asking me questions, I'm doing math, we present a formula, we've got to balance the formula, and the numbers are derived from the secret, but the secret's never shared. So it's computationally heavy, and that's why it was never widely adopted.
I know as the verifier that you know the secret that makes
Yeah.
these equations balance,
Yes.
putting it simply. And I guess I maybe I'm still thinking about it too much as like from an authentication angle,
Yeah. You've got to let
because
that
then I'm
go and
like,
think of it as verification.
yeah,
It's
yeah,
verifying something. Forget the authenticate. I know I've just done an authentication example of
no, that's
myself,
fine.
client server, but it's verifying you know something,
Mm-hmm,
which isn't
mm-hmm.
even what hashing is, right? Well, kind of, I don't know,
Sort of,
but it
yeah.
sort of does. But you still send something and
I
say
guess
there is
maybe
a
where we're
thing.
gonna go next is like, because then I'm trying to think like, how do I build something on top of this that has the kind of properties people like want to get for the use cases we talk about,
Okay,
right?
got you. Yeah.
Like, I guess I can construct like you say, we kind of share this equation or this kind of setup. Like we have this handshake where we kind of come to this shared
Mm-hmm.
like context to
Mm-hmm.
do this proof in, right?
Yeah.
Um, and I guess that's where you construct stuff or something.
Yeah.
Anyway,
It's from
whatever. I
there.
don't know.
But what it is it's a verification protocol that allows you to make make assumptions based on relatively solid, mathematically solid foundations. That's
Mm-hmm.
where you see the use cases come in, because if I know you've computed this thing correctly and I'm able to verify it without having to do the computation myself, what can I then build on that? In its
Yeah.
simplest form, it's, well, I know you are authorized to do said thing, or you're authorized to access said resource. But in reality, it can allow you to do a plethora of things. So basically, your imagination is your only limit, right? Which is why it became, okay, well, it got kind of crushed into, well, it got reduced into this shorthand of verify age without sending birthday, basically, because we can compute these
Yeah.
things and verify these
So I
things.
guess it's like the person, or the identity. I don't know if maybe I should just drop the word identity. Like the client that can submit a proof for this equation
Mm-hmm.
has, like in the authorization case, has the
Mm-hmm.
capability to do this, and then
Yes.
like each client has a different equation, a different context that
It
the proofs
depends
are
on how you
supplied in,
set it up, because
different parameters supplied to
you wouldn't
the
need to,
context, like.
in a very simple auth scenario. I don't think it wouldn't need to be. Well, they could be, actually. Yeah, everyone could have. Well,
Because
and they
like
would now know.
what I'm getting at is you need some way to differentiate client A from client B if you don't know the secret. Because usually you differentiate it by knowing the secret, right?
Yeah, true. So then,
So like,
okay, that's where the identification thing, I think, is tripping you up. Then, but instead of using
yeah,
it as it's not that I am differentiating between clients; it's that I am able to verify that these clients just know different things. That would be the more accurate way of
Okay.
using this rather than using it as a distinguishing factor. It's just I'm using it as a verification factor. You know something, not that you are different to something else. Does that
Okay.
make sense? So
Yeah.
don't collapse the two, separate them out. And
Yeah.
it comes out more and more, which is why, because you can have a bunch of people who all have the same attributes, but they still need to be verified. So they could all share the same thing.
Right.
So you can't use it as a distinguishing
That's true.
factor because it falls
Yeah.
down there. So yeah, so it's not widely adopted. C, Java, .NET, all those languages from the early noughties, giving people cold shivers right now as the PTSD. They're storing integers that are 32 bits, 64 in some cases, but minimum you need to actually satisfy what's known as the soundness principle, i.e. this is probabilistically sound in such that it's very, very unlikely that you're able to guess at the right answer and pretend like you know what you're talking about, is a minimum of 256-bit integers. So on 90s hardware, that's not happening. Hashing also was a great time. So it did the job for passwords in an authentication symbol. This is Web 2. People just want to upload their pictures and tell you what they ate for dinner. There's nothing complex going on here. I can imagine there are probably some military applications for that, but that's not my bailiwick, so I cannot tell you anything about that. But then also, yes, another issue is basically what would happen in some authentication schemas was they would tie the ability or your authentication, your ability to authenticate to the data that you were trying to access to as well. So if you lost the ability to authenticate, you also lost the ability to access that data. And it's funny because this kind of comes up again with 1Password, for example. They do use zero knowledge proofs inside, and basically your master password is tied to access to all your passwords. You lose your master password. They do have recoverability, obviously, outside of that. Do they actually have recoverability? Does Mastercard for this 1Password have recoverability if you lose your password, master password?
It depends on the setup.
Yeah, I think it does.
Like
It's
it depends
not.
on how it's set. Like if you're talking about a corporate setup, that's a bit different from
Yeah,
a client setup. Like if you're just like a kind of consumer
yeah.
client, I think the recoverability is entirely like offline stuff that you keep to recover. Like
Uh-huh.
it's not like a server side
Yeah,
recoverability because like you
Fair.
said that would compromise the zero knowledge thing. So you have like an emergency kit. On that emergency kit, you write down data, which is what lets you recover.
Recover your stuff. Got you.
I think enterprise use cases can be different,
Yeah.
and do kind of trade off the zero knowledge part for recoverability in
For
some
recoverability.
cases, I think, but I
Yeah.
don't 100% know that. Yeah.
Yeah, got you. So overall, what we've just discussed there is the 1985 version. In 1986, they were like, hey, can we not do this with all the questions? The interactive part. They were like, let's get rid of the interactive part. So what you have is interactive zero knowledge proofs. They're like, let's get non-interactive zero knowledge proofs. And they were
Which
basically
is what
able
you
to,
talked about before with
yeah,
like the larger answer space, right? The larger
yes,
like
the
solution
larger
space.
challenge
Yeah.
space. And so effectively what you're doing there is it basically does they basically do the handshake differently between what's known as my client server and Michael's prover server. They change the handshake in a way whereby you can just do it in one question, and so it's no longer interactive. And in some cases, actually, a question doesn't even need to be asked. You can just pre-compute the answer and say, look, this is the right answer. Don't worry about it. I've computed this program or this calculation correctly. Again, still large challenge space, i.e., you're still talking about large integers, 2 to the 256. So this is very large integers that computers can't really handle. But at the same time, as I said, the zero knowledge proof is effectively a family of types of protocols, and it can be used in different ways. We kind of just hinted at that with the 1Password. There are a bunch of different applications that came along before we get to blockchain world, which was, for example, in 90s, you had DRM, digital rights management. For anyone who is not our age, we should just leave that there. This was an interesting part. This was, I mean, let's talk about Sony rootkitting everyone's Windows PC because they wanted to make sure that you had a license to play a song or play a video. And this is very much the most obvious, well, the most probably the most frequent interaction people come across with embedded DRM right now is HDMI. I can imagine, where it has a little trusted platform module chip. Well, actually, no. Apple made it everyone, you got the secure enclave. That counts as a
Mm-hmm.
TPM. So yeah, Apple's made TPMs and Samsung made TPMs, which is what you authenticate to when you're doing Face ID, Touch ID. You authenticate to your TPM. TPM has a token, and that's what goes off to the surface. TPMs back in the day were very basic. And by the way, there was massive uproar. Another tangent. I just want to say there was a massive uproar about TPMs in personal computers from the computing community. Now we just accept it as a fact. And so one of the issues that came up with DRM services or DRM'd services and programs was that they used the TPM in order to actually decrypt or sign things or check that a signature was correct. It depended on, we won't go into the
Mm-hmm.
details of any implementation, but you also had a remote service that actually queried your TPM to make sure you had the ability or had the license or hadn't tampered with the game. And
Mm-hmm.
these TPMs are burned basically like firmware, basically like ROM almost effectively, where they're burned with a unique ID. And so one of the biggest issues with TPMs going into personal computers that we had in our community was, well, then this fact basically acts as a super cookie for the device, because any remote services that query this TPM are able to track you as you install whatever service or whatever game
Mm-hmm.
or play this or access whatever website. Because I think, yeah, ActiveX even had DRM embedded in it. I think, like, someone can correct me on that. So yeah, so that was where Zero Knowledge came in, because they were like, okay, well, we need to be able to do anonymous attestation without tracking people. So they implemented this thing called direct anonymous attestation, where they would where you could
Wow.
validate the manufacturer certificate on the TPM device without sending identifiers to a centralized server. So
That's quite the story.
it is. It's nuts, because guess what it brings us to? Privacy. People cared about privacy back in the 90s and the early 2000s. And it's also why I kind of steered you away from the identification thing and back to the
Mm-hmm.
verification thing, because privacy is all about verifying certain facts without revealing those facts really and truly. Privacy is about, if you're going to have the facts, keep them, only access them when you need them to, or verify them without actually having them, because that's what advanced privacy should look like in our day and age. Right now, me sending pictures of my passport, which I have to do a lot, I'm just going to let that one hang in the air, shouldn't really be necessary. What you should be able to say is, can I verify this person actually has a passport and it's a valid passport without asking them
Yeah.
to send it to me?
I think from the privacy angle, it's like, yeah, there's often a delta between what can prove the thing that needs to be proved and
Mm-hmm.
like what the thing that needs to be proved is,
Okay,
right?
go on. Explain that.
It's yeah, I mean, it's like all the examples you hear. It's like, okay, like we need to verify that this person's over um 25 or whatever. I don't know why I chose that. I don't know that anybody needs to verify that
It's
specific
because
age.
we're 25, Michael. It's because we're 25.
Yeah, that's right. Nobody check on that. Uh, and the way I do that is by showing, documentation of when I was born, which
Mm,
is like more data,
yeah,
which like reveals more data than is necessary.
yeah,
So there's like a delta between um, what needs to be revealed and what is revealed,
yeah.
or what is able to be revealed to prove it. I think
Okay,
it's the
got you.
same
Yeah, yeah,
thing.
yeah.
The same thing you're talking about with like the licensing stuff. Like,
Yeah.
what you need to prove is that
Um,
this machine
yeah,
possesses a license,
yeah,
and just because of the way it works or whatever, like that ends up including an ID or whatever, or with the
yeah,
passport, right? You need to prove this person has
yeah,
this nationality,
yeah,
and in order to do that, you also reveal address, name, whatever, just because that's
yeah.
bundled in with the documentation. So like, yeah, like
Exactly.
a lot of privacy is how do you manage that information delta
Yes, that's a great way of
responsibly,
exploring. That is a
right?
really good
Yeah.
way of putting it. It's a succinct way of putting it. And so that's one of the major applications, again, just in computing. So you've got that direct anonymous attestation for TPMs and DRM enforcement. You have subway cards. I'm not going to get into that one because that one's still a bit confusing. But long story short, subway cards on any mass transit system. So your New York subway, London Underground, Canada, Toronto's one, which I've forgotten what it's called. That is disgusting of me. I'm
You
sorry to my
forgot?
Toronto.
How could you forget the
How can I
TTC?
forget TTC? Thank you, because I never used it, mate. That's why. I'll be honest. We work from
What?
home. I never needed it.
Oh,
We
yeah.
work from home,
Okay.
right? Like I think I
That's
caught
strange to
that.
me.
Just a random tangent. I caught that thing 4 times, 5 times in the 5 years we lived in Toronto. Anyway,
Wow. Okay.
so yeah, you got subway cards as well, and again, they were all working off non-interactive zero knowledge proofs. And so this is where I, again, in my research bit, and as Michael has we've jumped ahead, but basically I realized this is, from a security perspective, this is a great privacy tool. It's not great for authenticating people. It's great for actually protecting and enforcing privacy, as you said, with that information delta. I need to prove something. Do I need all of this data in order to do that, or can I do it without revealing pretty much anything? Zero knowledge. And so that is kind of where we get to at this point, because now it's 2010 and Bitcoin has been around for, I think, a year at this point. And anyone who knows and has listened to any of our podcasts, you'll know that most of the blockchains we talk about, in fact, every blockchain we talk about on here is a public blockchain. We don't really deal with the private ones because they're private. But a public blockchain, and what makes it public is you can see all the data about all the all the engaged parties. So the wallets, you can see what's in a wallet. Oh, you've frozen, Michael.
I'm frozen.
Oh no,
Am I
you're back. Okay, cool.
Whew.
Fair enough.
I was just very still.
That was extremely
locked in.
That was you just zoned out there. Oh man, that was locked in indeed. So yeah, but where was I? Right. Fast forward 2010. Bitcoin has already been released. People are buying all their Bitcoins. People are sending their Bitcoins all over the place on a public ledger, which means you know where the wallet, you know the wallet address, who's sending, well, you know what wallet is sending what to whom. And people very quickly realize it's obvious. They're like, well, what if I don't want people to know what I'm sending and where? And so this is when someone was like, hey, I read this white paper from 1986. And it called these things.
That's how all good things start.
That's how all good things, right? Because let's not forget, the Bitcoin white paper relied on a bunch of old cryptography from the old times as well. I think it references it if you watch it, if you read it. And so this is where people started.
Yeah, I mean the whole Merkle tree thing.
Merkle trees are an old concept.
Another flash from
100% flash from the past, indeed. A blast from the past.
Blast from the past. That's what I mean.
So yeah, so they dust off zero knowledge proofs and optimize it such that the receipt, or basically the proof of the zero knowledge computation, is very, very small, because they need it to be done. They need it to be, don't want it to be run, don't want it to be computationally heavy. It needs to run on nodes, which is nodes.
So
are what
do they just like find a better way to do it? Like
they basically optimize
their ability to do this?
Yes, they effectively optimize it so that it's basically, the proof isn't as big as it would normally be in the old school non-interactive ZK proofs, and they call it.
They just think about it harder, and
they think about it harder. I'm not going to go into the details of how they got there. I'm not even going to talk about the history. But basically, what you have is a small receipt verification.
They went into deep reasoning mode or whatever.
That one tickled me more than it should have. And so basically, it creates a receipt verification that can be run on a node, because obviously it needs to be validated on one of the nodes on the blockchain in milliseconds. Otherwise, it slows down the entire chain ledger updating process. And their invention became known as succinct non-interactive arguments of knowledge. So we've gone from interactive ZK proofs to non-interactive ZK proofs to ZK snarks. Succinct non-interactive ZK.
Now that it has the nice branding, it's ready for takeoff now.
Jesus Christ, exactly. And so basically what you have here is it's optimized for proving, or basically it's optimized for privacy. ZK snarks was invented, and they created a brand new blockchain product off the back of that, which is super cool. So yeah, and then you get things like, okay, no, I'm not even going to jump ahead there. So then obviously 2015 or 14, Ethereum comes into being. And then not too long after that, you have Solana, which also comes into being. And they're like, okay, we want to optimize for speed of computation. And as you know, blockchains are basically really complex Merkle trees, which Merkle trees are kind of like hashes built on top of hashes. And
they're computation heavy. That's
they're
the
very
whole thing.
computation
That's
heavy.
why you have all the ASICs flying in
Yes,
their
that's right.
farms and all
That's why
that.
you've got
Yeah.
your Lightspeed A6 trying to figure out all these math questions. And they're like, okay, but how about they squinted, tilted their head a little bit, and they're like, okay, if we want to speed this up, we need to compress this computation. I know what we can do. We can use ZK, zero knowledge proofs, to compress computation, because if you remember correctly, you've got these computational heavy Merkle trees. If we just take them offline and basically say, okay, do the computation over here, then update the ledger over there, we can get away with that because you don't need to verify the math by running it. You just need to verify the answer. And we've got these snarks now, so we can compress the all of the transactions that came before into one receipt. And we know that none of the transactions have been tampered with, which obviously is how a Merkle tree
Mm-hmm.
is
Mm-hmm.
defined and works, because we've got the ZK proof that this hasn't been tampered with, and the chain updates quicker. So you can basically imagine batch processing. You take a bunch of transactions, put it offline, run those transactions, make sure that they're actually correct, and therefore they can be added to the ledger and the chain, do the
Mm-hmm.
verification proof, and then add it back to your actual secondary chain, so to speak. And this is where you come up with the concept of ZK rollups, zero knowledge rollups. So again, you've got your Ethereum chain. It's running slow because there's all these nodes and all these all the nodes are updating the chain. How about you take some of those nodes offline, actually create this thing called a sequencer, which takes all the transactions, batches them up, runs the computation quite quickly, creates the zero knowledge proof so that you know that the math actually works out on all these transactions, and then just add the receipt to the chain.
And what is the zero knowledge part doing there? You know what I mean? Like,
The
I don't know.
computation. So it's basically the zero knowledge part is I can trust the proof without having to have seen all the computation operations that got you to that proof.
Okay, okay, okay. Yeah. Okay.
So
That
that's
does make
where it is.
sense.
And that's the head
So it's
flip.
like, and that's where you talk about compression, right? I think we had a little side conversation about this
Yes, we
earlier
did.
too. Like you're using the fact that the verifier needs zero knowledge,
Mm-hmm.
like only needs zero knowledge in order to like compress the information in a way.
You're dealing with the fact that the verifier only needs to know that the prover did the math
Yes.
correctly. So the prover in this case is your sequencer, which is your little group of nodes who have been adding all these transactions to the blockchain in their way. So the prover has to say, this computation ran correctly without being tampered with. These transactions are all valid. Here's the proof of it. And then you go back to your original chain and it says, okay, cool. I can run faster now because you took some of those transactions
Yeah.
offline.
The proof verifies
So the proof verifies
without knowledge
without knowledge
of
of the
the
computation.
transaction of the
Yes.
computation.
Yeah.
Yeah.
And
Transactions
that's
may be
where
the
you
wrong word there. Without knowledge of
transactions
the
the wrong word.
computation. Yeah.
It's crazy. I mean, I'll be very impressed if our listeners are staying with this right now, because this is wild and we've got notes. So basically, you've basically what it's done is the zero knowledge part is proving that you've got the right answer, but I don't need to know how all the math and all the
Yeah.
computations.
And yeah, I think this is what I messaged you, right? Like this is kind of neat in that, yeah, like we're used to like kind of breaking your brain out of the way it wants to think about zero knowledge, which is like in that identity authentication way. In this case, like
Yeah.
the property of zero knowledge is actually being used, it sounds like, as a compression, as what enables compression to happen.
Yes, 100%.
Because you're saying this knowledge, you're not saying I'm trying to hide this knowledge from you, don't know
Mm-mm.
this knowledge or whatever. You're saying this knowledge is not necessary.
Yes.
Here's a proof that proves what you need to know.
Yes.
All this other like heavy computation and storage and like space that takes up is not necessary.
Yes.
And that's what enables the roll-up compression to happen.
That's what enables the roll-up. So this is why you have Ethereum as a base chain, and then you have these zero knowledge roll-up chains known as layer twos, where they're basically that compression gives you speed. And that's what Solana has done as well. It has ZK compression as well. The same thing. Basically, the compression gave them speed, and that's why their processing times on transactions are way quicker than Bitcoin's, for example. So, like if you move something on Solana, it takes seconds. If you move something on Bitcoin, as I did earlier today, it's 13 minutes because it obviously has to be added, computed, and so forth. So, yeah. And then to bring this up right up to the present day, A16Z have released something called a jolt, which is kind of crazy, and I'm still trying to wrap my head around it, because what you
Yeah.
got to understand about the ZK world is it's not computational, it's arithmetic. And so you have to think about it differently. Instead of thinking of it going binary through and or and logic gates such as that, it actually goes through these things called arithmetic circuits that operate on really large numbers. So these mathematical formulas and the values that are being plugged into them have to be selected from a basically a set of numbers, and it can't be
Hmm.
1 to n because that's an infinite field and your computer doesn't have infinite memory. So it's basically there's a special type of sets of numbers called, I think they're something about sigma protocols. I think they're called sigma protocols, where effectively you
Okay.
plug in a formula and you get a specific set of numbers, and then you run arithmetic circuits on these numbers to do the math and add new elements to the field. But it is a finite set, but they're very large, and it's a large set in of itself. Um,
Okay.
that converting that into binary is computationally horrendous. Apparently, this
Mm.
is what I hear. It's horrible to actually do that. And so that's another reason why it wasn't adopted. A16Z put 3 years of research into this and said, this is a really cool application, but we can't have people trying to translate. You can't have your developers trying to translate ZK proofs into binary code, into code as we understand it. They need an easier way to access this ability, because even on your layer 2, even on your ZK rollup chains, you're
Hmm.
effectively having to go through a translation process that can take days for your distributed app to be able to run on that specific, to be able to run optimized for that specific ZK rollup that you're running it
Okay.
on. So basically, A16Z put 3 years of research. Obviously, they partnered with some people, and they've come up with this thing called Jolt. And what they did was they effectively optimized ZK knowledge or ZK proofs to run on RISC-V, that can be compiled and run on RISC-V chips. RISC-V chips are your general purpose chips as we understand them inside your phone, inside your
Mm.
computer. And so basically what this allows you to do is it basically allows you programmers to basically pull zero knowledge computing and functions off the shelf like any other library and use them in their programs. And so in their apps, sorry, which is quite cool because they've basically made ZK proofs. They've taken it from the world of what was abstract cryptography, then blockchain, walled off gardens in blockchain. Well, ironically enough, walled off gardens in public blockchains, and put it in the world of the general purpose developer to use on your phone for
So, like, what
whatever
does that let
application.
a developer do?
I don't know. You asked the wrong
Okay.
question there, mate. Don't ask me that question.
Forget it. Cut.
So yeah, I mean, again, let's go back. Your question is actually quite simple. It's a little, how can I use, what can I do with a ZK proof? How does it help me? How does me knowing something ran computationally correctly help me do something with my app? And it really depends on your application,
Yeah.
really and truly. If it needs to know that something ran and was not, what's it called, tampered with, etc. So yeah,
Hmm.
basically A16Z, they released this in March of 2026. No, what am I talking about? That's wrong. They released the original Jolt in I think February of 2026. They did
Hmm.
it in such a way that it could be used as a compression mechanism, and it didn't have the privacy mechanism. They updated it a few weeks later and it now has the privacy mechanism as well. How it's different is obviously due to the details of how they've actually built it in the first place. But now you can basically get a ZK library for Rust or C, compile it on a RISC-V chip, and you're off. You're good to go. I hope that basically brings us up to date, and that brings us to the conclusion. And I'm hoping that people have walked away with some type of general understanding of what ZK proofs are and how they work, and more importantly, why we didn't hear from them for a long, long time, and then we did, because it's all tied to how they work in the first place. That magic of being able to verify a thing without actually having to see the thing is where we can all get lost in. But as I said, just think of it of it's the math, and there are certain properties of mathematical equations that allow you to validate, oh, this person does know a thing, or they did do the thing they said they did in a way without me knowing what the thing was in the first place, the
Yeah.
thing that was being operated on. It's crazy because people are using it, especially in the blockchain world, and as for compression and for privacy as well, because it is a great privacy mechanism. It's an amazing privacy mechanism. The fact that we're sending around passports and driving licenses over email and WhatsApp and uploading them into random portals could be a thing of the past if this thing was adopted more widely. And I have a feeling one of the reasons why it's not adopted as widely as it is within the tech community is because it's just so bloody hard to understand. I've met cryptographers who have told me, yeah, very few people actually understand the math behind it. And those are bona fide, dyed in the wool, very clever. I'm paid a lot of money to implement cryptography in apps, etc., who have told me that face to face. So yeah, that is our ride. That is our much delayed ride through the world of ZK proofs. This was a lot of fun trying to get my head around. Like even on nights where I was tired and couldn't be bothered, the geek in me loves this. And I hope you guys or all our listeners enjoyed it as much as I did. Michael, you asked great questions because you asked the exact same questions I asked while I was going through this. And yeah, I think we're going to leave it there. Michael, is there anything you want to add? Did that help you, Michael, actually?
I think it did help me. They still feel elusive to me,
Yes.
you know, like there's still something about them that has a bit of
mysticism.
mystique. Yeah.
It's a bit like,
which is cool.
yeah.
I like that. You need stuff like that. So
100%.
I'll continue to
I mean, dude, I'm still trying to figure out
live
how,
like that.
Yeah, 100%. Like it keeps the mystery about it. It keeps you on your toes. All right, that brings us up to an hour. That was a great chat. I want to say thank you for all those that have listened and made it through this far. And we will be back at some point soon. As I said, I'm in a spicy part of the world, so I'm not making any promises. But thank you for sticking with us, and goodbye. Thanks for listening. If you found this episode informative, feel free to check out other episodes where we discuss topics such as how and why destroyed tokens were brought back from the dead by Crypto.com, or our first ever episode where we riff on the reasons why we were inspired to start the pod in the first place. Also, don't forget to subscribe so you won't miss out when our next episode drops, and feel free to tell a friend to tell a friend.